Kumaravel, sir?
Yes, ma'am.
Sir, can we start?
Yeah, you can start.
Okay. Sir, I think echo is there from your side. Can you
There is
just
echo
mute for
from.
some?
Yeah.
Okay. Thank you, sir. So we'll start then. Okay. Good morning, all. Welcome to fourth day of AICT sponsored 1 week online short-term training program on VLSI design using Cadence tool, mixed signal VLSI design. Today we have with us our first speaker of today's session, Dr. S. Kumaravel. Dr. S. Kumaravel is Associate Professor at Electronics Engineering Department, Vellore Institute of Technology. He earned his PhD degree from NIT Trichy. He has published more than 26 papers in various journals and conferences. His area of interest are mixed signal circuit design and low power design. I, on behalf of organizing committee of STTP, welcome you, sir, and request you to start the session. Sir, I will share the sharing my screen. Yes, sir, you can now present. Your screen is
Thank you,
visible,
ma'am.
sir.
Yeah. Thank you, ma'am, for your introduction and giving me a good morning, all. I thank the management and my dear faculties to give me an opportunity to deliver the lecture on CMOS amplifiers for biomedical applications as a first session in the AICTE sponsored STTP on VLSI design using Cadence tools, mixed signal VLSI design. So coming to the topic of discussion, as my area of research expertise is on analog circuit design, I felt that we should have a system knowledge or some applications based circuit design has to be covered. So I have taken the application to be like biomedical application, and for that biomedical application, what are all the analog front end modules and how we need to design those analog front end modules we shall see in today's session. And I would like to emphasize the importance of analog design in today's digital world. So there are n number of analog blocks required to realize a system, and if those analog blocks can be done by digital, then we need not use analog. So we shall see whether these blocks can be realized in digital. Digital to analog converter, we can't realize it in completely digital pre-amplifier, power management circuits, reference circuits, phase lock loops, VCO. There are n number of, if you observe this diagram, the outer circle, it has got n number of analog and RF front-end blocks, right, which can't be realized in a digital fashion. So we need to go for analog one. If you take the mobile phone, almost 75% of the system is built based on analog and RF blocks. 25% is realized using digital block. Okay. So coming from that understanding, analog IC design is complex, and we should have a background in physics, electronics, information and control theory, signal processing, communication. All these concepts we should have a good understanding and variety of state-of-the-art solutions. So based on the need, analog circuits can be modified, and it is highly dependent on technology, and we should have modeling skills, and we should have expertise on EDA tools also. Even though all analog IC design is complex, but still it is necessary to realize an electronic system. So nowadays, most modern ICs are really big signal. We have both analog, RF, and digital. So it's called as mixed signal IC design. So this slide I have taken it from reference Francis Serra-Guerrales, Department D Microelectronics Systems Electronics, University Autónoma de Barcelona. So the perception of CMOS or MOSFETs in analog way and in digital way, we should have an idea. So in digital, we can visualize the MOSFET as a switch. Whereas in analog, the MOSFET can be visualized as a switch or as a current source or a variable resistance or a capacitance, dependent current source, diode, variable capacitance. So the visualization of the MOSFET itself is more in terms of analog compared to digital, where it is visualized only as a switch. So we know the basic. I am not going to the very basics of MOSFET device operation, but we know MOSFET is operated in three regions of operation: cutoff, triode, and saturation region. So to realize digital circuits, we need to use our device to be operated in cutoff and triode mode. Okay. In analog, all three modes of operation can be used. Specifically, we go with saturation region to design amplifiers, oscillators, all those blocks, comparators. Fine. So saturation is important in analog circuit design. So we know the IV characteristics of the MOSFET, and for various regions of operation, the drain current equation is given by this expression. It depends on the constraint. When VDS is less than or equal to VGS minus VTH, then the device is going to be in triode region. If VDS is greater than or equal to VDSAT, the device is going to be in saturation region. So as the technology, if you see the IV characteristic, like a parable or this dotted line, okay, it splits the region of operation into linear and saturation mode. In saturation mode, the drain current is almost constant. It can act as a current source in saturation region, whereas in linear region, it can act as a resistance. And our MOSFET is going to suffer from two second order effects. One is channel length modulation, and other one is body effect. So channel length modulation, due to channel length modulation, saturation region will have a slow peak. In deep submicron, if you observe CLM of this graph, CLM, channel length modulation, okay, this is going to be like constant, but due to channel length modulation, you will have a slope. Due to which the current is given as 1 plus lambda VDS, okay, the drain current equation. Body effect will come into effect if two transistors are stacked one above the other. So as I mentioned, that MOSFET will be operated in saturation region to realize analog circuits. So the small signal model of the MOSFET is shown in this figure. So the small signal model, we can. Is my screen visible? Is my screen visible?
Yes, sir. Yes, sir.
Yes, sir.
Yeah.
Yes, sir.
Uh, okay, so this is the MOS small signal model. You see the structure for NMOS, N plus. This is oxide. This is polysilicon. Gate, source, drain in a P substrate. NMOS. So this is silicon dioxide. This region is silicon dioxide. So it acts as an insulator. That's why MOSFET has got an high input impedance. It has got high input impedance. Okay, so it is left open. This is gate, drain, source. The current that is going to flow through the MOSFET is given as GM times of V and R0. This is in low frequency condition. This is in low frequency. Whereas if you observe the structure of the MOSFET, there exists some capacitance. The capacitance or so between gate to source, this overlapping capacitance, right? This one, right? And then this is P type and this is N type. It is going to form a diode, right? Right? So this is like bulk. P substrate, this is bulk, right? So this will be in reverse bias. This diode operates in reverse bias because bulk will be biased to the lowest potential. Lowest potential terminals. So it will be reverse bias operating diodes. We know that in reverse bias there exists a depletion capacitance in diode. Right? This depletion capacitance with respect to source and bulk is termed as CSB, and with respect to drain and bulk it is given as CDB. And this overlap capacitances are given as CGS and CG. Okay, so there are four capacitance that exist in the MOSFET, which will have its effect on high frequency domain because we know the capacitive impedance is given as XT is equal to 1 by omega C. So as frequency increases, the impedance gets decreased. Okay, it may act as a short circuit for high frequency. If it is going to act as a short circuit at high frequency, the device is going to be no more MOSFET. Okay, so we should consider about the high frequency effect also when we are analyzing the MOSFET. Right? So based on that understanding, here we have got CGD, CGS, CSB, and CD. So this is a high frequency model of the MOSFET. So now we need to go with the analysis. So in MOSFET, we have got the basic configuration. We have got a it's a 4-terminal device. Gate, drain, source. This is going to be bulk. Even though it's a 4-terminal device, we will consider about the 3-terminal predominantly gate, drain, and source. Based on that, we have got common source, common drain, and common gate. So this is basic configuration. Based on this configuration, if you want to design a high gain amplifiers, we can go with common source. So common source, 2 stages. We can go to design a high gain amplifier. So we'll call it this as cascade amplifiers. Whereas CES, CG, if you go, it will be termed as cascade amplifier. Okay. So 2 types of amplifiers, high gain amplifiers are there: cascade amplifier and cascade amplifier. Right? High gain amplifiers. It depends on the configuration. Amplifiers circuits are connected. These are basic single stage amplifier. In single stage amplifier, let me go with a very common configuration. This is a common source amplifier. Okay. This is a common source amplifier. So we can draw the small signal circuit. So since this is a common source amplifier, the source has to be grounded. The source has to be grounded. This is going to be GM times of V in. Here you are ensuring that the transistor is in saturation region. Okay, gate, drain, source, and this drain terminal. From this drain terminal, RD. Okay, this is V out. This RD terminal is connected to VDD. In small signal, how this VDD has to be ground? VDD has to be connected. It has to be grounded. It has to be grounded. Why it has to be grounded for small signal? Why DC voltage need to be ground, and why DC current source need to be open? Any guess? Any guess? Am I audible? Any guess that you can make out of it? Why we need to connect the DC voltage to be ground?
You're audible, sir.
Yeah, why DC voltage need to be ground? So from VD, yeah, anyway, I'll also just share my thoughts. If I am wrong, you can also correct me. Okay, fine. So from VDD, we are going to draw a force current. Okay, this current can be of any value. Okay, I can source 1 milliampere or 2 milliampere, whatever may be the current. Okay, this VDD is going to be constant. Okay, this VDD is going to be constant. Right? So voltage remain constant for various values of current that is going to be drawn from the power supply. Right? So if you take the slope of it, what? Y by X. So if you take 2 points, okay, I1, I2, V1, V2. So V1 minus V2 by I1 minus I2. V is what we were saying, 0. 0 by some current. It's going to be 0 only. Okay. V by I term is what? V by I term is nothing but resistance. So
Resistor.
resistance is 0. Okay. So for DC voltage, here what I mean, the small signal current, here it may go to any value. Okay. So even though whatever may be the variation, my DC voltage is going to remain constant. So we are grounding the DC voltage. Okay, fine. So hence we are grounding the DC voltage. Whereas for current source has to be left open, I am saying. So if I am going to see a constant current source, this is one configuration. Okay. So what I have to, how I have to draw the small signal. So this is gate, drain, and source. Gm times of V. Right? Here now the drain terminal, it is connected to current source. VDD is grounded. from drain. Okay, this current source is going to be left open. Why? Whatever may be my input voltage, the current that is going to flow, because I current, there is no other path, right? So I will not increase. I have set this to be 1 milliampere. It will be always 1 milliampere only, right? So what I have to do, so let me take a slope. Whatever may be the voltage, my current remains constant. Again, taking the slope y by x, I1 minus I2, V1 minus V2. So it is going to be what? 0 V, right? It is going to be 0. So I by V is 0. So R, if you are going to take represent it as a resistance, R is equal to 1 by I by V, 1 by 0, infinite. Okay, so the current source is going to offer a high impedance. Okay, it is going to offer a high impedance. That's why the current source is going to be left open. If you observe here, this current source is left open. It will not be connected. Okay, it's left open. Do you agree with me? Do you agree with me?
Yes, sir.
Okay. So that's why we are making the DC sources to be ground or open circuit. Now, to analyze the frequency response, till what value I can apply, till what frequency I can apply the input signal. So we would have studied about control systems, transfer function. In control system, H of S, A to 1 plus S by omega Z1 plus S by omega Z2, etc. divided by 1 plus S by omega P1, 1 plus S by omega P2. So this is the transfer function of a system. So we should correlate our circuits to this transfer function. Right? So how we can correlate? In this circuit, so if you observe any circuit, right? So first we will be drawing the small signal Vm times of V in R naught RD. This is going to be V out. V in. So some source resistance. Plus this has been applied to gate, drain, source. So if you get an expression AB, K is the low frequency DC gain. Okay. K we need to determine. So that K is like AB is equal to V out by. So what is V out? V out is equal to the current that is going to flow, GMV in. It is flowing like this, right? So minus GM V in times of R naught parallel RD. R naught and RD are parallel. Okay. So V out by V in is equal to minus GM R naught parallel RD. So we can write approximately equal to minus GM RD. This is the low frequency DC gain. Okay. So now we are going to draw the Bode plot. Frequency. Bode plot has what? Magnitude plot. and phase plot. Now we will try to understand the magnitude plot. So it is going to be AB magnitude, so GM RD. So how long the gain is going to be constant? Any guess? It's a very basic thing only. Please, do you think the gain remains constant always as frequency increases? No.
No, sir. When the
Ah,
frequency is increased after a certain point, the gain will start decreasing.
why? What that point we used to call?
So generally we call cutoff frequencies or
No. After a particular frequency, the gain starts
gain
rolling
will
off.
decrease.
Right? Why? Why it has to decrease? Why it has to decrease? So there comes. Now we'll go back to the transfer function. Right? This A is
Sir,
not going to
parasitic
remain.
capacitors are
That's
the things.
capacitor. Yes, exactly.
Yeah.
So now we have seen in MOSFET as frequency, high frequency model of MOSFET. So we have got CGD, CGS. Okay. With respect to bulk, this is going to be grounded bulk. So CSB. Then this is drain terminal PD. Right? CGD and CGS. This CSB we can neglect because both the terminals are connected to ground. So this also connected to ground, this also. So capacitor means two dissimilar metals with asymmetric charges, right? So if two parallel plates with unequal charges, here negative, here positive, separated by an insulator forms. Whereas here it is maintained at the same charges, negative charges, right? So this capacitance we can neglect. So CDB, that capacitance also is going to be there. Bulk is going to be. Okay. So now in circuits, we need to identify, one should understand how many nodes are there in this circuit. How many nodes are there in this circuit? How many nodes? So if you observe this circuit, here there is a node means what? Two or more network elements meet at a point, forms a junction or a node. So here this is node 1. Here it is node 2. Two nodes are there. Two nodes are there. So in circuit design, each node contribute to a pole. Okay. So the pole frequency is given as omega p or fp, whatever it is. So it's going to be 1 by product of resistance and capacitance seen at that node. Okay. At node. Product of resistance and capacitance seen at the node. So coming back to the diagram, here you have got two nodes are there, omega P1 and omega P2. So what is the resistance and capacitance that is with that node to identify? Okay. So here also if you see here 1, this is 1, this is 2. This is for pole. How a 0 is contributed? Feed forward path. If there is a feed forward path that connects input to output, a 0 will be existing. Okay, so 0 will be contributed based on the feed forward path. So why there is a feed forward path? If you observe this circuit, there is a feed forward path that is given by CGD, right? So there is going to be 1-0 formation. Okay, this CGD directly connects the input to output feed forward path. Okay, so if you want to realize the transfer function with conventional approach, it becomes a tedious process. So we need to write the KVL and KCL, and then we need to figure out what is the transfer function. So in order to simplify the derivation, wherever the feed forward path is there, we can apply Miller's theorem. We would have studied about Miller's theorem, right? We would have studied Miller's theorem. If an impedance is connected between two nodes, X and Y, it can be split into X node and Y node, provided same current is going to flow. Here I current Z2. Okay, same current has to flow. Then only we can split the impedance that is going to be associated with X node and Y node. So now what is Z1? We can write, since the current is going to be same, Vx by Z1 equal to Vx minus Vy by Z. So you take Vx as 1 by Z1 equal to 1 minus Vy by Vx by Z. So Z1 is going to be Z by 1 minus Vy by Vx. That is output. It's nothing but gain. So Z by 1 minus AV. Similarly, Z2. Vy by Z2 equal to Vy minus Vx divided by Z. So we can write this as 1 minus Vx by Vy by Z. Okay. So Z2 is equal to Z by 1 minus Vx by Vy. We can write as 1 by. Okay. So the impedance that is going to be associated with individual nodes can be calculated based on applying Miller's theorem. So it helps our analysis to be much simpler. So now coming to the point, now this CGD, we can write as 1 by SCG, right? This is the impedance. So now we will split the capacitance that is going to be associated with 2 and 1, and then we will figure out the transfer function. So RS this is CGS, V in, or GM V in, R naught, RD, then TDB. Because source and bulk are maintained at same potential. Okay. So here V out. This CGD I am going to write this is Z1 equal to Z by 1 minus AV, right? Here Z is 1 by SEGD, right? So we have to write 1 by SEGD into 1 minus AV. So this capacitance will be there. So CGD into 1. Here it is going to be CGD into 1 minus Okay, so this is going to be the capacitance that is going to be associated with 2, 1, right? So already this EGD was there. This has been flipped like this. So now we now have this. So now we have to, there are no feed forward paths. So in our transfer function, 0 will not exist, whereas pole is going to be there. So omega P1 is equal to 1 by R naught parallel RD. That is the total resistance into CdV plus CGD into 1 minus 1 by CV. This is the capacity. Omega P2 is equal to 1 by RS to VGS plus VGD into 1. Right? So this is the pole frequency. Now we can write the transfer function as H of S is equal to minus GMRD divided by 1 plus S by that omega P1, right? Omega P1 S by omega P2. So where omega P1 is going to be 1 by RD parallel R naught to CdV plus CGD into 1 minus 1 by CG. Okay, similarly, omega P2 1 by RS into CGS plus CGD into 1 minus CG. So this one you can. So in our transfer, if a pole is going to exist, what will happen? There will be a decay of minus 20 dB per decay, right? So a pole is going to exist means there is going to be. So this pole omega P or omega P2 based on the values of capacitor, which is going to be the dominant pole. Okay, based on the values of resistance and capacitance seen at the node. Okay, so the pole near to the origin is termed as dominant pole. Okay, per decade it will have, and where it touches, it is going to be unity gain bandwidth. This is going to be your bandwidth or F3 dB. Okay, so unity gain bandwidth is equal to F minus 3. So we can apply our input signal up to this frequency. Till that frequency only you will have an amplification. Beyond which it will be, there will be no amplification. Are you able to follow? So this is the very basic concept. Based on this thing, the single stage amplifier, there are some drawbacks. So we will go with the differential configuration. We'll go with the differential configuration, and this is cascode configuration. So this is a MOS differential amplifier frequency response analysis. Okay, using cascode amplifier. M1 is a CS, M3 is CG. This is cascode configuration. Right? So how many nodes are there? Half circuit. We have to go with half circuit analysis. Right? If you go with half circuit analysis means that means circuit is symmetrical with respect to M1 and M2 pair. Okay. So how many nodes are there? Based upon that one, we need to write the pole frequency. So in this thing, you have got X, Y, right? X, Y, and output node. 3 nodes are there. At X node, it is given as 1 by RS into CGS1 plus 1 plus GM1 GM3 into CGD1. PY 1 by GM3 into CDB1 plus CGS3 plus 1 plus GM3 by GM1 into CG. Omega P out equal to 1 by RL into CGB3 plus CG. Okay, 3 poles are. This is just for our understanding. Okay, how to identify the poles in the circuit and how to get the expression of the pole frequency. So now coming to the actual concept of today's discussion, we are going to analyze, we are going to study the design of analog front-end modules for biomedical application. So we need to understand the characteristics of biomedical signal. So the characteristics is shown in this diagram. So if you observe the signal amplitude of biomedical signal, it ranges from few nanovolt to few millivolt, and the frequency is up to 10 kilohertz. Right? So we need to process this signal. So this is the biomedical application analog front-end module, low noise amplifier, programmable gain amplifier, and ADC. And in today's topic of my discussion will be on this low noise amplifier and ADC. Okay, programmable gain amplifier and filter I am not going to touch upon that one. So low noise amplifier and ADC. So what is the requirement of instrumentation amplifier going to be used in as a front end amplifier in the biomedical recording system? So this low amplifier should have noise less than 3 microvolt RMS. Power should be in microwatt, and it should have a gain of 50, greater than 50. Bandwidth should be less than, because the biomedical signal bandwidth is 10 kilohertz. Okay, and it should have a high pass filter characteristic to block the DC electrode offset. It should have high input impedance, high CMRR, PSRR, and high dynamic range. So these are all the constraints related to this instrumentation amplifier requirements. Now, we are going to build this circuit using CMOS circuit. We know technology is scaling down. So what will be the impact of technology scaling in analog design? So merit is, as the device size is getting shrink, it will lead to high level of integration, and FT of the MOS device is going to get increased. Whereas demerits is signal to noise ratio is going to decrease, and intrinsic gain, this one intrinsic gain, GM or not, is going to get decreased. Okay, this is going to get decreased. Right? So if it is going to get decreased, if you observe, so the gains is given as GM intrinsic gain, generalized expression GM or not. Okay, as technology scales down, it is going to get decreased. If you are going to realize the op amp in lower technology, you will achieve only lesser gain. Okay, so to achieve more gain, we need to increase this factor. So GM has to be increased, means ID current has to be increased. Okay, then only GM will be increased. You understand, right? So power consumption is going to be, so as technology scales down, to realize analog circuits, power consumption is going to be increased. Whereas in digital circuits, P is equal to PV square F, PVDD square, right? If VDD is scaled directly, power consumption is going to get increased. Whereas in analog, power consumption is going to get. So the front-end amplifier is shown in this figure. For this amplifier, this is capacitively coupled instrumentation amplifier. The transfer function is given as C in by CF by 1 plus SCL C in GMCF dot SF into 1 plus RFCF. This is a high pass filter characteristic. This is a high pass filter characteristic, and this is going to be your bandwidth. Okay, This is the pole that defines the bandwidth of the system. Okay, and this is Cin by Cf is the K, low frequency K. Right. So we are going to design now. My topic of today's discussion will be this one. We call it as GM block. Okay, GM block. How we can design. So there are so many topologies: telescopic cascode, folded cascode. Okay, predominant GM blocks or OT, operational transconductance amplifier, are called as telescopic cascode. Telescopic cascode means stacking one above the other. Folding, this is the folding node. Okay, this is folding node. Two predominant architectures are used for realizing that GM block. We need to understand the gain equation, gain and a small signal analysis of this topology. So to understand this topology, let's take folded cascode. Let's take folded cascode topology for our analysis so that we can understand in a much better manner. So this is the folded cascode topology. So here, if you observe, we can draw the half circuit. So if you ask for differential signal, this is going to be grounded because here you will apply equal signals in amplitude but opposite in phase. So at this point it becomes virtual ground. So M1 is going to be ground. Here you are going to apply. Okay, this is VDD. I'm going to draw the half circuit. This is M3. So let's name this BB3, BB1, and BB4. Here you are going to take Vout. Okay. So now for the small signal, what we will be doing? First, grounded, right? This is going to be grounded. This is going to be grounded. This is going to be grounded for small signal. All the DC voltage sources are going to be grounded. Here, G equal to 0. Okay. VSG is 0. The current that is going to flow, the small signal circuit is going to become, so I'm going to draw this as R0 because if you see gate, source, drain. So for a MOSFET, GM times of VG. If VG is equal to 0, there will be no current. Only R0 will be there. So the R0 will be over here. So R03 that will be ground. This is going to be grounded. So and here if you observe VGS equal to 0, so this is going to be 9. And here the input signal M1. Okay, so here you are going to have V out. Now we need to determine the gain GM to R out. This is the small signal gain GM into R out. So we need to find GM and R out. So to find GM, short circuit output node, apply test signal at the input. Okay, at the input. So if you see here, we have to short this. We need to short this output node, right? So let's short this output node. So we are going to short this output node. Okay. So I out is a current. Short circuit means current is going, voltage is 0, current is going to flow. Right. This I out current is going to flow, is generated based on applying V. Okay. So I out is equal to GM1 times of V. Same current only. This is high impedance or not. Okay. All the current is going to flow through this. Okay. So I out by V in is what? Going to be GM1. Okay. I out by V in is nothing but GM. Okay. Similarly, to find R out, circuit the input node and apply the signal at output node. So if you see this one, so we need to short circuit the input node and apply test signal. So if you apply this one, input signal VGS equal to 0. VGS equal to 0. M1 can also be realized. This M1 can also be realized as R01. So I'll write R01 parallel R03 by 7 R09. So here you are playing Vx and Ix. So here looking up and looking down. Okay. So Rx equal to Vx by Ix, which is R down parallel R up. Okay, this is R up and R down. Okay, both are symmetrical in nature. Only thing here a NMOS transistor, here PMOS device. So now let's try to figure out the output impedance looking down. Okay. This M7 R09 VF and IX is the current that is there. So we will draw the small signal GM7, VGS7, R07, VF to R09. Okay, gate, this is G7, E7, this is S7, right? So here VGS7, IX is the current that is going to flow over here. Okay, even though it's going to get divided IX at this node, some current is going to flow here and some current is going to flow here at the end at this node IX into R09, right? So gate is ground. Gate is VGS. How we can write? VGS equal to VG minus VG is 0. So it's going to be minus VS. So it is going to be here. This part, this one is going to be minus VS7. Okay. To negate, to overcome this negation, to remove this negation, we can change this direction of current like this. Okay. So at this node, now IX, right? IX plus this GM7, VS7 will be the current. Here it's going to be GM7, VS7 is the current. IX plus GM7 is the current that is going to flow through this resistor. So applying KCL, here KVL along this path, KVL along this path, we can write Vx is equal to Ix plus GM7 VS7 to R07 plus Ix into R09, right? So again, the GM7 here at this node, it gets flipped, right? Ix into R09. What is VS7? Ix to R09 R09. So if you take common as Ix, right, you will get R07 plus GM7 R07 R09 plus R09. So R down is equal to Vx by Ix. That is going to be R07 plus GM7 R07 plus R09. So this term is much higher. Okay. So approximately R09. That is going to be the down impedance. So up impedance also both a similar structure. So we can write as GM5 R05 R01 parallel R03. So if you observe, this is also cascode GM5 R5 into RO1 parallel RO3. So this is going to be R out. So the total gain we can write it as GM1 into GM7 R07 R09 parallel GM5 R05 R03 parallel R01. So this is the gain. Now coming to the frequency response analysis. How many nodes are there? We need to identify. There are at the output there is one node, and at the cascode node one more node. All right. So omega P1 is equal to 1 by R out into CL, and omega P2 is equal to 1 by RP2 into CP2. That is the cascode node. So we need to draw the parasitic capacitance, right? So let's try to figure it out. So how many nodes are there in this circuit? So here there is one node, here there is one node. Okay. Right? So let's name this is output node. This is cascode node. So we need to find out what is the pole frequency. So omega P1 we can write as 1 R out to CL if it is going to drive the capacitance, load capacitance R out into CL. Okay, this node is going to be dominant. That means once a particular frequency is reached, this node will become, this will be shorted to ground. This will be shorted to ground. So what happens? This is going to be ground. For calculating omega P2, okay, this is gate and drain. Right? For a transistor, if gate and drain are maintained at the same potential, gate and drain are maintained at the same potential. This is termed as diode connector device, and its impedance is given as 1 by GM. Okay, 1 by GM. So 1 by that 1 by GM5. Okay, this 1 by GM5 parallel RO3 parallel to that capacitance, that is going to be capacitance PSG GM5 by DC. Okay, the whole frequency area. So RP2 equal to 1 by GM5. So if you substitute GM5 by CP2, and the unity gain bandwidth is AV into Z. So GM2. Okay. At the same time, the bandwidth also should be less than 10 kilo. So the analysis is over. Now for us, noise. Noise is very, very important. Okay, I heard from Professor Raso that noise characteristics has been previously in the previous session it's been handled, but to have a quick recap on it, our MOSFET has got thermal noise and flicker noise, right? The thermal noise is given as 4 kT gamma by GM, okay, voltage in terms of voltage, thermal noise. Flicker noise is given by K by Cox into WL into 1 by F. If you see the noise characteristic, so at low frequency, flicker noise dominates. And at high frequency, thermal noise is dominant. So flicker noise is at low frequency, at biomedical signal or at less than 10 kilohertz. So flicker noise is going to be contributed. Okay, and so if you want to reduce the flicker noise, we can go with PMOS device. Okay, we can go with PMOS. So we know the mobility of holes and electrons. Mobility of electrons is greater than mobility of holes. Okay, it is going to be 2 points. So in the drain current equation, ID is equal to half mu n Cox W by L VGS minus VTH whole square. This mobility, okay, this mobility, if it is an NMOS device, it is going to be higher. The same current, if you are going to realize using PMOS device to match with the mobility degradation, this W by L we will be increasing. That's why PMOS will be having low flicker noise. So to design biomedical amplifiers, right, we should use PMOS as the input device. Are you able to follow? Are you able to follow? Why PMOS device I am suggesting to use? Are you able to follow? Please respond.
Yes, sir.
Yeah. So we need to design with PMOS circuits. So these are all the things I can skip as suggested by Professor Rathod. I just want to So we need to calculate the input referred noise. For the biomedical amplifier, the input referred noise voltage should be very, very minimum. Okay. How we can calculate the input referred noise voltage? Vn square equal to AV square Vn. Okay. So Vn out square bar divided by AV square, it gives you the input referred noise voltage. So if you observe for a common source amplifier, you find that it is inversely proportional to Vn square bar is inversely proportional to 1 by Gm. Okay. How we can reduce the input revenue? It implies that the transconductance of M1 must be if you maximize the transconductance, the input referred noise can be reduced. So to maximize the transconductance, now in the literatures, there are topologies available. There are n number of topologies available. I'll go with that one. And moreover, slew rate also we should know, since we are going for biomedical application, the time, the low frequency, so the time constant can be more. So the current that is going to charge that output node can be very less. Okay, it can be very less. Fine. So ISS by 2, this can be very less. At the output, we can have very less current. It doesn't contribute to the GM. So M1, whatever M1 current is going to draw, that is going to contribute to the GM. Okay. So we can reduce the output current also. And there is one more technique called source degeneration technique, where your GM, unless unwanted transistor, if the GM is very high, we can minimize that GM. Minimize that GM. That is source degeneration. So there comes the topology named as recycling folded cascode. Recycling folded cascode. As I discussed here, if you see PMOS device, this is a PMOS type folded cascode structure. We need to improve the transconductance. So to improve the transconductance, what they have done is M1 is split as M1A and M1B, and M2 is split as M2A and M2B. Okay, splitting for the same current. Similarly, this M3 transistor is split as M3A and M3B. M4 is split as M4A and M4B. Okay, this is a current mirror. This part is current mirror. Okay, so this current mirror, how we are going to improve the GM. That's what we are going to see. Here actually IB is the current. Now IB by 2, IB by 2, all the current we are not sourcing more. Same current. For the same current only we are going to analyze it. Okay. So now the small signal analysis M1 and M2 split into M1A, M1B. M2 is M2A, M2B. Similarly, M3A, M3B, and M4A and M4B. Gain is given as GM into R out. GM is I out by E. So I out is what? What will be the I out current now? I out will be GM1 times of A, right? GM1A and GM3A. Two current, this current and this current, right? Right? It will enter and it will go to I out. So you can write as GM1A V in plus GM3A Vx minus, because Vx minus. What is this Vx minus? It also should be Vn plus, right? Vx minus. How this Vx? So Rx equal to 1 by Gm3, Vx plus equal to Gm2B, Rx, Vn. Vx, Vn minus is what? This minus, this minus, and Vn minus, we can write Vn plus, because one signal is going like this, means this is Vn plus, this is Vn minus. If I apply minus to this thing, this will become thing Vn plus. So if you observe, Vx plus equal to Vn plus. So based on that, GM1A plus GM2A plus. So based on that, GM equal to GM1A plus GM2. So GM equal to GM1A into K plus 1. Here K is 3. If you take K is equal to 3, 4 times of GM1A. 4 times. That is nothing but 2 times of GM1 in the previous architecture. Because here the current is ready, IB by 2, IB by 2. IB, this IB, M1, IB current is going to flow. Whereas here IB by 2, IB by 2. Okay. This, due to IB current, you will have GM1. Okay. For the same IB current, here we are getting like times of GM1. So the gain is, the transconductance is also enhanced, and the transconductance is enhanced. The input referred noise voltage is going to be less compared to the folded cascode amplifier. Compared to folded cascode amplifier, for the recycling folded cascode architecture, the input referred noise is going to be very less. Okay, so like that, so many topologies. One more topology has come. This is improved recycling folded cascode. Improved recycling folded cascode. So here also, if you see, it is K by A times the GM is enhanced. The purpose is we need to reduce the input referred noise voltage, for which the transconductance has to be maximized. So these topologies are all helpful. Now coming to the low noise design. So as I mentioned, for biomedical application, we need not design high-speed amplifier. We need not design high-speed amplifier, because at the output node for biomedical application, high-speed amplifier is not required. Okay, slew rate can be, so the current that is going to flow through that output node can be minimum. Okay, it can be minimum. So we need not target about that one. So we can reduce the current that is going to flow through the output node and add that current to the input transistor. This is a folded cascode architecture. This node, these transistors are source degenerated. This M3 and M4. M3 and M4. Here it draws more current. So GM is going to be more for this transistor, due to which the noise contribution of this transistor will be very high. So to reduce the noise contribution of this M3 and M4, we are going for source degeneration resistor, so that the GM of M3 and M4 can be. So this is proposed in the year 2007, current scaling and source degeneration. Okay. And then the same architecture has been for the recycling folded cascode. For the recycling folded cascode, if you observe, I have added source degeneration resistor. So if you see this thing, if you add source degeneration resistors to this thing, it becomes like folded cascode, current scaling and current splitting. So here also the GM is more, the M3A, M3B more current is going to flow, due to which the noise contribution of M3A and M3B will be more. To minimize that one, we are going for source degeneration resistor. Source degeneration resistor used to minimize noise contribution. Okay. For whatever the transistor you are applying source degeneration, it will reduce the noise contribution of the transistor. So my part is for the improved recycling. For improved recycling, I have used source degeneration resistor during my PhD, and then I derived the equation noise referred noise voltage and the performance. If you see, the noise is input referred noise. It is 2.99. The capacitance I have used as 10 picofarad. Then for a power consumption of 1.5 microwatt. Why power is very, very important in nowadays? Implantable chip has come into effect. So when you implant a chip in human body, the battery should draw very less power, right? Or else battery has been drained. Every time we can't do surgery and change the battery. Okay, it should draw very less power consumption. Okay, this is for single preamplifier. So multi-channel biomedical recording systems are available. There, where you will have some 10 channels, 16 channels, like that. So each and every channel has got one individual system like this. So every channel has got this individual channel. So power consumption, we should see that it is very, very minimal. Okay. So with this thing, I will stop today's first session, right? And with the performance metrics also, NEF, all those things we have to see. Maybe some 5 minutes we will have some queries if you are having any doubt. Okay, 11:20 now. Maybe we'll have end up the session in another 5 minutes per session. If you are having I have just gone through the concepts how you can design a low noise amplifier. One is we need to maximize the transconductance, and other one is whichever transistor is going to contribute to the noise. For those transistors, if source degeneration can be adopted, we can adopt. Okay. So we need to figure out once you have completed what is the device size you are using, expression of noise voltage, in which region you are operating. Okay, all those things we need to quantify. Okay. And these are all my references. So all these are my references. Maybe you can ask queries for 5 minutes. Any queries?
Yeah, participants can unmute and ask the queries. Or they can write in chat box.
Yeah. So we have one more point I would like to suggest you, especially for biomedical application. There is a journal IEEE transaction on biomedical circuits and systems. Please refer papers from this journal so that you will have a very good knowledge of how to design analog circuits for biomedical application.
So one question is in chat box
Yeah,
regarding bandwidth requirement.
bandwidth.
Yes.
For bandwidth requirement, as I said that the F3dB, if you observe the biomedical signal characteristics, 10 kilohertz. 10 kilohertz is your band till this signal. You need to design an amplifier. Say, for example, if you are going to design an amplifier only to process EEG signal, so your bandwidth should be in hertz, right? ECG signal, it should lie between some few hertz, some 1 hertz to 100 hertz. Okay, if it is EMG, 100 hertz to 1 kilohertz. If some action potentials, if you want to process it, then it should be up to 10 kilohertz. It depends on the biomedical signal, which.
So in case of tissue impedance, if you have to find what is the frequency it will come, and hello, hello,
हा मॅम बोला ना. हॅलो.
सरांचा आवाज येत नाही.
हा सरांचा आवाज म्यूट झाला.
So actually
Hello?
you are not visible. Your voice is breaking.
Mostly the application, the bandwidth
Yes, yes.
requirement.
But
Yeah.
for tissue impedance, for ET, I mean,
Hello.
yes, sir.
Can you pardon? Yeah,
Yes, for
pardon. What's your question?
so actually I'm getting echo. Okay. So for finding tissue impedance in case of a ETI, what is the bandwidth requirement and how we can define a signal for a circuit for it? So you are muted.
Yeah. So you are using a electrode to sense the signal. So skin from the, you will be placing the electrode in the skin. So that forms an electrode skin interface that is going to contribute to the high impedance. That's why we are going to, we should design an amplifier in such a manner it should avoid that electrode skin interface. Some offset voltage will be generated. We should design a circuit in such a manner it should have a high pass filter characteristic to remove that offset voltage. So that high pass filter characteristics is given over here. This MH1, MH2, this CF. This will remove the DC electrode offset, which is contributed by the electrode skin interface that generate an voltage that is called as electrode offset voltage. And one more thing I will also like to share my screen. So there are challenges of physiological signal measurements using electrodes, right? So how the electrode tissue interface, the model, circuit model. This is in-depth analysis of the biomedical amplifier. Now we are targeting only about the circuits. Okay, how we can design a very low noise amplifier. Okay, so this PDF will give you a much better idea about the interfacing issues, electrode skin interfacing issue. The model, how we can model that one electrode in terms of circuit element. Are you able to follow, ma'am?
Yes, sir. Yes.
Any
Sir,
other
can you show
questions?
the first page of this paper? I will take a photo of it.
Challenges of physiological signal
Yeah, thank you,
measurements
sir.
using electrodes.
Thank you, sir. Any other question from participant side? No question, sir. Can we take 5 minutes break, sir?
Ma'am, can we take 10 minutes?
Okay, no
Can I
problem, sir.
take?
So we now at
By
11:30.
11:30 now, 11:30, 11:40 I will join, ma'am.
Okay, sir. Okay, sir.
Thank you, ma'am.
Sir, voice is not clear. And caller. Sir will rejoin.
Sir is rejoining, I think.
Yes.
No, sir, you're not audible. Yeah, muted your mic, I think.
इसके पहले तो ठीक था ना?
हाँ, इसके पहले ठीक था सर, म्यूट है उनका माइक अभी.
अच्छा अच्छा अच्छा. Yes. Yes, sir.
Yes, sir. तो इनके पहले इनका आवाज अच्छा था, लेकिन पता नहीं अभी ईयरफोन का. So screen is not visible.
वापस ब्रेक हो रहा है.
तो आई थिंक उन्होंने ईयरफोन नहीं लगाया है.
अभी आया थोड़ा तो ठीक था.
Hello.
Yeah, sir. Now clear.
Now clear? Okay, sir. Okay.
Yeah.
Because,
Now you. Yeah.
okay.
I was thinking what has happened. Morning first session was okay. That's why a little bit out.
Sir, you can make it full screen. Yeah, make it full screen. Yes,
Can I start, sir?
yes, sir. Yes, make it full screen, sir.
Hello?
Yes, sir. Yes.
Yeah, okay, fine. Okay, so to process this analog signal, we need analog to digital converters. Similarly, to process digital to analog signal to analog conversion, we need a digital to analog converters. So how we can, all signals that are available in nature or analog in form. Okay, so to process that signal, we require an ADC. So we can say that ADCs and DACs is the interface which connects the physical world to the digital world. So the first front end block of the analog signal is going to be the sample and hold circuit, and after sampling that corresponding sampled output will be measured with a reference voltage, compared with the reference voltage, and accordingly the digital bits will be given as output. Similarly, that DAC analog will convert as a digital code, whereas in digital to analog converter, the input will be in digital fashion, and that will be converted into an analog signal using this digital to analog converters. So there are two types of ADCs. One is how we are classifying means Nyquist rate A to D converters and oversampling A to D converters. We will go as of now for this session with Nyquist rate A to D converters. Nyquist rate A to D converters is we need to sample the input signal at 2 times of F in the input signal. The sample and hold characteristics, sample and hold circuit, how it is, the characteristics will look like. So the dotted signal is going to be the analog signal. At each and every instant of time, the signal will be sampled, and that sample will be compared with the reference signal, and the digital conversion is going to happen. So this is for sample, and for a particular time hold. Okay, at that level the signal will be hold for a moment. Okay, the output characteristics of sample and hold output is shown in this figure. In track and hold means till the switch is going to be on, it will be tracking the input signal, and then it will be hold the signal at the highest value. Okay, so here why we require a op-amp connected in unity configuration. We are realizing a switch. If the switch is turned on, your input signal is going to be passed to the output, and it is going to, the capacitor is going to charge to the input value. That itself is going to be the sample and hold circuit. But why we are connecting an op-amp to realize the sample and hold circuit means, if there is no op-amp, if the switch is going to remain open, when it is going to be turned off, this capacitor equivalent circuit, it has got a resistance. There will be the charge that is held at the capacitor will get discharged. Okay, to overcome the discharge of charges in the capacitor, if you connect an op-amp, it has got a high input impedance, so the capacitor will not be discharging, so it will be holding the charges till the signal is converted into a digital signal. That is the reason we are connecting a op-amp. Okay, fine. If there is no op-amp, the charge may get discharged from the capacitor. After to overcome that only we are connecting an op-amp in unity configuration. So first we will go with the digital to analog, the fundamentals. What are all the performance metrics that we need to understand? So resolution. So what is the resolution? Whether it's a 10-bit DAC or 8-bit DAC, how many bits you can present as input. So those things we will be calling representing in terms of digital. How many bits we are representing, that is termed as resolution. Okay, so where V out is the analog or voltage output, V reference is the reference voltage, and V out is given equal to F into V ref. This F is given as whatever the digital bits we are giving, for that the equivalent digital number will be given. Okay. N is the fraction defined by the input word D, that is n bits wide. So the number of input combination represented by the input word D is related to the 2 power n. So if n bit resolution you are having, 2 power n combinations are going to be there. Accordingly, the input word D is going to be there. Okay, D is equal to 2 power n. The full scale voltage of the DAC is given as 2 power n minus 1 divided by 2 power n into Vf. So if you, for example, for a 3-bit resolution DAC, if 00 means 0, right? 001 means 1 by 8. So the full scale. So you can write as 2 power n 3-bit, all right? So 2 power 3 minus 1 divided by 2 power 3. So it can go up to 7 by 8 times of Vref, 7 by 8 times of Vref, the full scale voltage. So 001 means 1 by 8, 010 means 2 by 8. The equivalent D is nothing but 2. 010, the decimal equivalent is 2. 011, the decimal equivalent is 3. That's what F is equal to, like that we are V out equal to F into Vref. Okay, so this thing, the DAC characteristic is shown in this diagram, and to characterize the DAC, the metric term as differential non-linearity we used to call as DNL. Okay, why we use this performance metrics means, ideally speaking, this 001 means 1 by 8 is the analog voltage. It is going to be the analog voltage for 001. But it is realized using some analog components. We know that analog components is going to be a non-ideal component, which will introduce some errors, that will introduce some errors in the DAC. Okay, so to characterize it, we need to identify what is DNL. Non-ideal components cause the analog increments to differ from the ideal values. How it can be calculated means, the difference between the ideal and the non-ideal values is known as differential non-linearity. Okay, actual increment height of transition n to a particular word to the ideal increment height. So if you observe this, determining the DNL for the 3-bit non-ideal DAC whose transfer curve is shown, assume V out V reference equal to 5 volt. So this is the characteristic for a DAC we have got. Now we need to calculate the DNL. DNL, what they have given, it is actual increment height of transition. Actual increment of height minus ideal height, right? 001, the actual ideal height also is going to be 1 by 8. Just a minute, I have got sorry. Yeah. So for 001, the actual height and ideal heights are same, right? So it is going to be 0. DNL, we can represent it in terms of LSB. So we know 1 LSB is equal to Vref by 2 power n. LSB is equal to Vref by 2 power n. Based on that, we can quantify that LSB as 0.25 LSB, 0.5 LSB, 0.75 LSB, like that. So 0, 0, 1 is 1 by 8. The ideal height and the actual height are same. For 0, 1, 0 also, the actual height is 2 by 8. Ideal height also is 2 by 8. That's why 0 LSB. It is 0 LSB. Whereas for 0, 1, 1, if you see, it has to be at actual height, ideal height should be at 3 by 8. The dot should be at 3 by 8, ideal height. But actual height is, it is going somewhere in the middle of average of 3 by 8 plus 4 by 8 divided by 2. Okay. So some 0.5 LSB is higher than the ideal height. The actual height is 0.5 times higher than the ideal height. So we can write as 0.5 LSB. For the, if you look at the diagram at the downside, bottom left hand side, 0, 1, 1, you have got 0.5 LSB. Similarly, for 1, 0, 0, the characteristic, it is 4 by 8, right? But the height is, the actual height is only 0.5 times, right? Ideal height is 1, it should be there. Okay. The ideal height should be like 1 LSB, but only 0.5 LSB. So it is minus, right? Minus actual height minus ideal height. Actual height is 0.5 minus ideal height is 1 LSB. So it is going to be minus 0.5 LSB. Similarly, for 101, the actual height is only 0.25. Okay, and the ideal height should be 1 LSB. So 0.25 minus 1, it is going to be minus 0.75. So for 101, it is minus 0.75 LSB. Similarly, for 110, the actual height is 1.75. Ideal height is 1 LSB. So 0.75. So the DNL curve. So from this, what we understand is, from this DNL curve, for all digital bits, there is some increment in analog voltage we were able to follow, we were able to understand. So the curve is monotonic, incremental fashion we are seeing. So there won't be any chances of missing analog values, provided this DNL values, a trade-off we should have. DNL value should not exceed more than 1 LSB or less than minus 1 LSB. Okay, so that defines the monotonicity. So if the DNL for a DAC is less than minus 1 LSB, then the DAC is said to be non-monotonic. Non-monotonic means, which means that the analog output voltage does not always increases as the digital input code is incremented. A DAC should always exhibit monotonicity. If it is exhibiting monotonicity, then only we can say that for as the level of the digital code is going to get increased, the analog voltage is also getting increased. Okay. Right? Similarly, there is one more performance matrix called as integral nonlinearity. This is also a static characteristic of DAC. It is defined as the difference between the data converter output value and the reference straight line. How it is calculated means, a reference straight line will be drawn from the first and the last output values, and then we need to find out the difference between the reference straight line and the output value. So this one, INLN, should be output value for input code N minus output value of the reference line at that point. INL should be less than, should be always plus or minus 0.5 LSB. That INL value should lie between plus or minus 0.5 LSB. So a reference has been drawn, ideal line. So from that line, the ideal height, similar, what is the difference? So output for 001, now for this thing, it is somewhere 1 by 8 plus 2 by 8 divided by 2. It's lying in the middle. This value minus the reference line point, right? So for 001, there is 0.5 LSB. So if you observe the diagram at the right hand side, this part, so it is going to be for 001, it is going to be 0.5 LSB. For 010, similarly for 010, it is 0. Reference line point and the output value point are lying at the same position, so it is 0. For 0, 1, 1, it should lie somewhere here, but 0.5 LSB, so 0.5 LSB. For 1, 0, 0, it is exact, so 0 LSB as INL. Whereas for 1, 0, for 1, 0, 1, it is the actual, the reference line, this is a point, but the output is minus 0.75 LSB. Okay, so it is given minus 0.75 LSB. For 110, it is exactly lying at the reference point itself for 110 and 111. So the INL is lying between plus or minus 0.5 LSB, means there will be no missing code. Here it is for one code. For one code, it is coming minus 0.75. So there will be some missing analog value. So for reconstructing the analog signal from the DAC, it will not be like a smooth waveform. Okay, the drawback. If INL value is not satisfied, a smooth waveform analog signal you will not be getting. That's the drawback. So there is one more characteristics, offset. So offset, if you are having due to analog components for 0, 0, we expect 0 as the analog value, but we are getting 1 by 8, some value, that value is termed as offset. Okay, for a digital input of 0, 0, 0, the analog value should be 0, but there is an offset exists in the analog output voltage, that is termed as offset. Similarly, gain error. A gain error exists if the slope of the best fit line through the transfer curve is different. So ideal slope and the actual slope, if there is a difference, then it is termed as gain error. So these are all some performance metrics used to evaluate the DAC. And signal to noise ratio for Nyquist rate A to D converters, SNR is 6.02N plus 1.76. Based on the number of bits, the signal to noise ratio is going to be defined. And dynamic range is defined as a ratio of largest output signal over the smallest output signal. So largest output signal is 2 power n minus 1, and the smallest output signal is going to be 1. So dynamic range we can calculate. So similar to that, for ADC also we are having the performance metrics, but the thing is that here for DAC we don't have quantization error. Okay, quantization, what does that quantization error in the sense, if you are going to apply 0 as the analog input voltage, your digital output is going to be 0, 0. Okay, till 1 by 8 of the V reference, your input, even though you are increasing your analog voltage, but your digital code is given as 0, 0, right? Till so that means the difference between the input and the staircase, voltage at the staircase, is going to be defined as the quantization error. So that quantization error, again, it is going to be given in terms of LSBs. So 1 LSB from 0 till 1 by 8. If you extrapolate the points from 1 by 8, 2 by 8, 3 by 8, the quantization error is going to be 1 LSB. If the quantization error is going to exceed 1 LSB, then there is going to be some missing codes, right? So this quantization error, we should consider that it has to lie within plus or minus 0.5 LSB. Okay, so that's why here, since the analog input is an infinite valued quantity and the output is a discrete value, an error will be produced as a result of the quantization. This error, known as quantization error, is defined as the difference between the actual analog input and the value of the output given in voltage. So QE is V in minus V staircase. Okay, that staircase voltage can be based on the decimal value of the digital code into LSB. VLSB will be given as the V staircase. So to make the quantization error that is not exceeding plus or minus 0.5 LSB, we shift the curve. the staircase by 0.5 LSB to the left. To the left, we will be shifting the curve by 0.5 LSB so that you will have the quantization error centered about 0. Okay, centered about 0. The purpose of the comparator for analog to digital converter means we are going to realize after sample and hold, the next block is going to be the comparator. So comparator, if you are going to use plus minus, you are having V reference. This is going to be V in. Okay, this is going to be your V out. Okay, V reference we will be giving. If the comparator is going to have some offset voltage, if it is going to have some offset voltage, we may think that the reference voltage we are giving as 1 volt. But offset voltage is say for example some 0.2 volt. It's going to be say for example 1.2 volt. Okay, fine. Whereas your input voltage, if you are giving like 1.1 volt, your reference is 1 volt, it has to be actually compared with 1.1 volt, but the reference, actual reference will be like 1.2. Again, we will be giving it as 0. It will not be like 1. Okay, so to overcome that offset voltage only, we are shifting the curve with an offset shifted by 0.5 LSB. That means we can have 0.5 LSB maximum, 0.5 LSB as offset of the comparator. So this characteristic, by shifting it, we can draw the quantization error. Okay, and similar to the integral non-linearity, similar to that, here also we are having DNL and INL, differential non-linearity and integral non-linearity. Here it comes in step width, whereas in DAC we have calculated step height. Here it is width in the horizontal manner, whereas in DAC we have got vertical manner, right? So actual step width minus ideal step width. From that we can calculate the DNL. Okay, so this is the characteristic of 3-bit ADC if you are having. Fine. So the quantization error plot is shown below. Now we need to calculate the DNL and INL. Okay, so DNL and INL, just a minute, I will. Yes. So DNL of, for this figure only, we are going to calculate the DNL, right? So DNL of 0, DNL of 0 equal to 0, because it is 0 only. For this value, it's going to be 0. For DNL of, also note that the step width associated with 001 and 100 are equal to 1 LSB. For 001 and 100, this is equal to ideal step width. Okay, remaining step width and all, it is unequal. Okay, so we need to calculate for the remaining thing. DNL2, DNL of 2 means for the digital code 010, that is 2. Okay, it is 1.5 LSB. The ideal step width is minus 1 LSB. It's going to be 0.5 LSB. Similarly, DNL of 3, DNL of 011, that is the decimal number is 3. So the actual step width is 0.5. Ideal step width should be minus 1 LSB. So it is minus 0.5 LSB. We will be calculating the step width like this, and we can plot the DNL value, and we can see that the DNL value doesn't be less than minus 1 LSB. If it is minus 1 LSB, it is not a monotonic ADC. That means missing code is going to happen. Okay. So here, if you see the 2 LSB, so if you having there are going to be missing code. That's why missing code, how it will be happening means, if the DNL is going to be less than -1 LSB means you will have the missing codes. And similar to that DAC, here also integral nonlinearity you are finding. In integral nonlinearity, again between first and last value, we will draw the reference line, and then we will identify the difference between the actual step heights. Okay, so that is going to be the INL. And for ADCs also, and offset error and gain errors are there. So these are all the performance metrics that we should know how we are going to characterize the DACs and ADCs. Okay, I hope these terms already would have been familiar. If you are not familiar, the references I have taken it from CMOS Circuit Design and Layout by R. Jacob Baker. I will show you the reference also. You can get the information from the particular textbook. Now we will go with the DAC architectures. First thing is DAC architecture. So how we are going to, the input may be presented in any fashion, right? For the digital to analog converter, the digital input can be given as binary, or it can be given as thermometer, or it can be given as a gray code or 2's complement. The decimal number of 0 can be represented in binary if it is a 3-bit DAC 00. If you want to represent the decimal number 0 with thermometer coding, it should be binary. If you are a 2 power n minus 1, 2 power n minus 7, you have to represent in 7 bits. Okay, the thermometer coding for a 3-bit binary is going to be equivalent is 2 power n minus 1. So 2 power so it is going to be 2 power n minus 1 from binary to thermometer. Okay, n bit binary if you are having 2 power n minus 1 representation. So 3 means 2 power 3 minus 1, so 7 bit. So if you observe 1, 2, 3, 4, 5, 6, 7, 7. 0, 0, 1 means 0, 0, 0, 1. 0, 1, 0, 1, 1, 1. Okay, like that, the number of ones will be incremented. Okay, so gray code, I hope everybody knows that one, right? So there are so many DAC architectures. We will go to the recent DAC architectures are current steering DAC. It is one of the very important architectures in today's scenario. To understand that current steering DAC, first we will go with the basic resistor string DAC. Okay, resistor string DAC. This resistor string DAC can be realized either using thermometer code representation or binary switching. The switch array can be like thermometer. Okay, the 3-bit DAC means yes, 7 switches you will be having based on individual switches. Based on the thermometer code, one S0 will turn on first, then S1 will turn on, S2 will turn on, S3, like that. If you are going for binary switch, so here you will be having LSB to MSB. The switch configuration is aligned from LSB to MSB, right? And then the switching and the number of switches used to realize the binary fashion will be very less compared to unary type or thermometer, unary or thermometer, because if n bit, if the number of bits is going to be more, we will have n number of switches. So at the output, what happens here is the capacitance. Here the capacitor, here, because switch is realized using MOSFETs, right? Everything will be in triode region. So this CGD, CGD. So the capacitance effect is going to be more. Capacitance effect is going to be more means T is equal to R into C. The conversion speed is going to get reduced. Okay, the demerits is conversion speed is less. Whereas here, if you observe in binary switch array fashion, the capacitance is less at the output. Capacitance is less at the output. So the conversion speed is going to be high. That's what here it has been mentioned. The one problem with the converter output is always connected to the converter output is always connected to 2 power n minus switches that are off and on. So for larger resolution, a large parasitic capacitance appears at the output node, resulting in slower conversion speeds. So hence we go with binary. A binary ensure that the output is connected at most n switches. So thus increasing conversion speed. That is the parasitic capacitance at the output node we are decreasing. Okay. And with respect to area also, we should see another problem with the resistor is the balance between area and power dissipation. Always when you come for circuit design, we need to look upon with area, power and speed. Okay, so how we can and we should try to minimize the passive components. So in resistor string, resistor will occupy more area. Okay, so huge area will be required to realize this area. And this DAC. So to overcome that one, for low resolution applications, maybe we can go with resistor string DAC. Even this resistor can also be modeled using MOSFETs. In CMOS process, resistors can also be modeled. This is one simple conversion error for 001. What all the switches will come into effect. Okay, so this is in UG we will be studying the resistor DAC in this fashion. But when you come as a research, now we should look upon the characterization. What contributes the non-idealities in the resistor string DAC? We have seen INL and DNL. INL and DNL. This we should calculate so that whether monotonicity through mono maintained as we increment the digital code, we are able to find the increment in analog output voltage that we have to see using this DNL characteristic. Okay, fine. And INL, it has to be DNL should not be less than -1 LSB, and INL should lie between plus or minus 0.5 LSB. This is a constraint. So what contributes the non-linearity that we have to see. So this is an advanced research topic, mismatch errors related to the resistor string DAC. So always we can't say that a resistor 1 kilo ohm means it will not be like 1 kilo ohm. Always there will be some tolerance, right? The tolerance may be 5%, right? It may be 1.05 kilo ohm or 1.005 kilo ohm. If that is going to be happen, if delta R is going to be like 625 ohm, some 10 ohms is going to be added. The reference voltage here it is going to get changed. Accordingly, the conversion is going to be happen. Okay, so if this del Ri equal to 0, then there is no problem with it will be equal to the ideal DAC. Fine. If all the mismatch is going to be 0, then there is no issue on the mismatch. But ideally, it's not possible, right? So we need to calculate the issues with respect to this mismatch. So what is V ideal? What is the step? So I of Vref by 2 power n. This is the step height. This is the step height for ideal condition. Okay, when I is equal to 0 Vref. when I equal to 1 by 2 power n Vref. That's what we are seeing now. V out is equal to F times of Vref. F is equal to D by 2 power n. D is decimal value corresponding to the binary number. Okay, so I of Vref by 2 power n. So now we will include the mismatch. However, including the mismatch, the actual value of the ith voltage is sum of all the resistances up to and including resistor I divided by sum of whichever we may be targeting for the fourth node, but we have to include the mismatch that is available in all the resistors. So we have VI equal to Vref into sigma k is equal to 1 to I Rk by k is equal to 1 to power n into Rk. Okay, for that particular, see now if you are going to calculate for this voltage, reference voltage, at the numerator, these three values will be taken, the mismatch and the resistance in the three resistance will be taken divided by the mismatch that is going to be available in all the resistors. That's what it means. Okay, VA equal to Vref, K is equal to 1 into I, Rk divided by. So Rk we can write it as R plus del Rk, and this is going to be 2 power n into R, the mismatch. Okay. So now the denominator does not include any mismatch error since it was because all the resistances we have taken. So lower part will have positive mismatch, upper part is going to have negative mismatch, means it gets cancelled out. So that's why the lower part we are taking that there is no mismatch. Okay, the denominator does not include any mismatch since it was assumed that the mismatches sums to 0 as defined in equation 29.2. Okay, sum of mismatch corresponding to all the resistors is going to be 0. Okay, so for the numerator part alone, we will expand the equation Vref by 2 power n R into I into R plus sigma k is equal to 1 into I del R k. I of Vref by 2 power n plus expanding this equation we will get. So this part is going to be ideal. This is the ideal. So VI is equal to VI ideal plus Vref. Okay. So this is VI minus VI ideal. This is going to give you the DNL, right? So sorry, INL. INL is equal to VI minus VI ideal. So Vref by 2 power n sigma k is equal to 1 to I del R k by k. This is the INR. This value we have fixed it that it should be plus or minus 0.5 LSB. We have taken an example. If the INL value, if the resistor is going to have 2% matching, then del R k. Okay, mismatch is 2k 2%. If you are going to introduce it, is going to be 2 times of R. The negative mismatch is going to be minus 0.02. Positive mismatch is going to be 0.02 R. So INL maximum INL that we are going to get is half LSB, right? Half LSB into 2 power n percentage of matching, that is going to be 0.01 times of Vref. So if Vref is going to be 1 volt, it is going to be 0.01 volt. So we know that 1 LSB is equal to Vref by 2 power n. Okay. So based on the resolution, we can write Vref 3 means 2 power 3 Vref by 8. Right? So 0.5 LSB, if you take as 0.5 LSB means it is going to be Vref by 16. So Vref equal to 1 volt. 1 volt divided by 16. What you will be getting? 1 volt divided by 16. So it is going to be 0.0625. So 0.0625. So if Vref equal to 1 over here, it is going to be 0.01 only, which is lesser than which is lesser than this thing. So our INL, if you are going to have 2% mismatch in the resistors also, our INL is not exceeding 0.0625. You understand, right? So this is how we need to introduce the mismatch and then see to that the DAC is performing in a much better manner. Similarly for DNL, VI minus 1. Okay, so here also it should not be less than -1 LSD. So we are getting like 0.0. So the purpose of this session is, rather than again explaining the literature, which we may be aware of it in an advanced manner, how to calculate with respect to INL characterization has to be done. That idea I am delivering. Okay, right? Are you able to follow? Are you able to follow? This INL, DNL concepts, are you able to follow? Please.
Yes, sir. Yes, sir.
Yeah, okay. So now, current steering diagram, most advanced current steering digital to analog converter architectures. The purpose is in resistor string, we are using resistor. It's a passive component. Even though you are going to realize it using a transistor to behave like a resistor, but the area that is going to be occupied is going to be more. Okay, to realize a high value of resistance in the fabrication process, it is going to be difficult. So to overcome that one, we can go with current steering DAC. In current steering DAC, again, we can give you a digital input in terms of thermometer or binary code. Now in this architecture, if you see, we are giving it in thermometric code. Thermometric code. So as I was saying, that thermometric code, it's going to be 2 power n minus 1 combination for n bit binary. So from D0 to, if n equal to 3 means what we will be having 7, right? 7 current sources are required. 7 current sources are required. So D naught, here 2 power n means is 6, right? Here n equal to 3 means 2 power n 6, 8 minus 2. So D6, D5, D4, D3, D2, D1, D0. So there are totally 7 current sources are there. Okay, so 7 current sources we use to realize the current steering DAC based on the digital input, based on the word D0, 0 or 1. Accordingly, the switch, these are all controlled. This switch digital bits. Accordingly, the current is going to flow through the resistor. If you are connecting to the resistor over here, the current that is going to be flow through the resistor is going to develop some V out. Okay, so that is going to be the analog output voltage. But what is the drawback again to the resistor? These are all realized using current reference circuits. Current reference circuits. If you are going to realize 10 bit, n is equal to 10 bit. So how many current sources you will be required? How many current sources? 2 power n minus 1. 2 power 10 minus 1. 1024 minus 1. So 1023, from 0 to 1023 current sources are required. Okay, 1020. So the area is going to be more. If you take current to be some 5 microampere, each and every individual current sources to be 5 microampere. So 1020, the area is going to be more. So similar to the resistor string DAC, how thermometer to binary we are moving, here also we can go with binary type of current steering DAC. Okay, binary type of current steering DAC means 2 power n, I, 2i, 4i, 8i, 16i, like that. So if you are going for binary type of 2 power n minus, the largest value is going to be 2 power n minus 1. So this is going to be 1023i. So it will go like that, 4i, 8i, 16i, right, 32, like that it will be going for 64, 128, like one. So we will be requiring, the current value will be 1023 times of I. So what is the drawback in both this thing? One advantage of current steering DAC is the high current drive inherent in it. Since no output buffers are necessary to drive resistive load, these DACs are typically used in high-speed application. In current steering DAC, the resolution, based on the resolution, the architecture is going to change, whether it's a thermometer based representation you are going to give as input or binary type. So for example, they have taken a thing. For example, if a 13-bit DAC architecture was designed using this architecture, so 13-bit means if it is a thermometer code means how many things you will have. So 2 power 13 minus 1, right? 2 power 13 minus 1. So that turns out to be around 8,191 current sources will be residing on the chip. This is an insignificant with thermometer code. If you go with the binary weighted thing, you will have the size of the largest current source is going to be 4,006, but the number of current source is going to be very less, right? It's going to be very less. So even if the unit current I was chosen to be 5 mega, the largest current source is going to be 4096 into I. It is going to be 20.48 milliampere. Okay, so here we should have a trade-off. We should have a trade-off. If you go with the binary type of configuration, the current rating is very high. The current rating is very high. Power consumption is going to be more. If you go with unary type or thermometer code, if you take I to be 5 microampere, all the 8192 current sources will have 5 microampere current only. Do you understand? Fine. So what do you call that? If you go with this binary weighted configuration from 011 to 100, okay, if you go with this glitch will be, because all the switches will be simultaneously turning off and on for a particular instant of time. That will cause a substantial voltage spike. That will cause a substantial voltage spike will occur at the output. A glitch will be there. In this current steering DAC, the main problem is glitch. How we can overcome the glitch? This is one problem. So I have given idea that current steering DAC can be either realized using unary fashion. Unary fashion means thermometer binary fashion. So we've understood the drawback in each configuration. That's why now in today's research they are going with segmented type, segmented steering DAC. What in segmented means, LSB part they will be realizing thermometer and MSB part binary. Okay, they will classify the current sources with respect to thermal energy. So if it is an 8-bit, a 4-bit DAC I am going to use. Okay, 1, D3, D2, D1, D0. This 2-bit I will be using thermometric code. So 2 bits. So 2 bits means 2 power n minus 1, 2 power 2 minus 3. So I will have unary current source, 3 unary current sources. Okay, I. Similarly here 2. So 2 power n minus 1 I current sources we require. So 2 power 2, 2 power n equal to 2, that is 3 current sources we 2 power n minus 1 current sources, 2 power 2, so 3 current sources. So I, 2I and 3I. 3I current sources we will be using, so that the glitch avoidance can be overcome. Okay, this is some high research topic, but just have an idea that in current steering that segmented configuration will remove the glitches, will helps in removing the glitches. Okay, so with this as a DAC architecture, similar to the resistor string DAC, here also INL, DNL and all we need to calculate. Now we will go with the ADC's architecture. Okay, so in ADC architecture, the first and foremost architecture is flash ADC, right? Flash ADC, we require 2 power n minus 1 comparators. We require 2 power n minus 1 comparators. So if you look in the perspective of area, if you go with high resolution, n is equal to 10 bit, how many 1023 comparators are required? Okay, which is occupying more area and power. Whereas speed, simultaneously all the comparators are going to work, so speed will be very high. This is the high speed ADC in flash ADC. The conversion is going to happen at a single instant of time itself. Okay, so now we should have a trade-off. We should have a trade-off between area, power, and speed. So how it can be done? How it can be done? So there comes this flash ADC. Probably you will be knowing. I will go with one more type of ADC, two-step flash ADC, so that we will reduce the number of comparators. So if this is the architecture of two-step flash ADC, that is we are classifying as LSB ADC and MSB ADC. Okay, we are dividing the ADC into LSB ADC and MSB ADC. So what is the advantage? Here you can see the type of flash is a two-step flash converter or the parallel feed-forward. The converter is separated into two complete flash ADC. Again, it's going to be flash only. This LSB ADC and the MSB ADC. Again, it's going to be the flash ADC only. Whereas the first converter generates a rough estimate of the value of input, and the second converter performs a fine conversion. That means what is this is coarse. This is coarse, and this is going to be fine. Fine coarse. Maybe we would have seen in our lab equipment. Coarse and fine regulations, okay, in power supply. To that one. Here in this architecture, the advantages of the architecture are that the number of comparators is greatly reduced. How it is reduced? In flash ADC, we require 2 power n minus 1 comparators. Whereas here the comparators is because we are dividing into LSB and MSB 2, right? So 2 into 2 power n by 2 minus 1 comparators. So 8 bit if you are going to use, 8 bit, so 2 power 4 by 8 by 2 minus 1 into 2. So 2 into 2 power 8 by 2, 2 power 4 minus 1. So 16 minus 15. So only 30 comparators are required. Only 30 comparators are required. Whereas compared to for the same 8-bit in flash ADC 255. Whereas here only 30 comparators are required. So we are reducing the area as well as the power consumption. But speed is limited by it's getting reduced by 2 compared to flash ADC because 2 steps are required, LSB and MSB ADC. The speed is a trade-off. So depending upon the application, for biomedical application, sampling speed is not of that much required. Only resolution we are going to target. So when you target for resolution, area and power, if you go with the 8-bit resolution based ADC for biomedical application, we will prefer this ADC compared to flash ADC. Okay. Still, is there any opportunity to reduce the number of comparators going to be used? Fine. With respect to application, we can see. Okay. So first we can try to understand the conversion. After the input is sampled, the MSB bits are converted by the first flash ADC. So from the sample and hold, MSB bit will be generated, and again that MSB will be converted using DAC. Okay, as an analog signal. The result is then converted back to an analog voltage with the DAC and subtracted with the original input. That is termed as residue. The result of the circuit known as the residue. This is multiplied by 2 power n by 2 gain. The gain of this is the gain of the amplifier. So we need to design the gain of the amplifier in such a manner it is 2 power n by 2. Okay. The multiplication not only allows the two ADCs to behave, but also increases the quantum level of the signal input into the second ADC. And then the second ADC produces the least significant bits through a flash conversion. So if you see an example 0 to VDF, you are giving the input voltage immediately. This will be first converted, right? This will be first, this input is lying between 0, 1 to 1, 0 means this part alone will be again converted. Okay, right? So this is the first conversion identifies the segment in which the analog voltage resides. This is also no, okay. I'm sorry, I have written over here. This is coarse. This is coarse, and this is fine. Okay, this is fine. So first coarse conversion MSB will, and then that is multiplied into 2 power n by 2, subtract and expanded by 2 power, and then the final resolution is going to happen. Okay, this is also called as two-step algorithmic flash ADC. You can also see one problem. So 4 bits of resolution, make a table listing the MSB V1, V2, V3 and the LSBs for VN to 2, 4, 9 and 15. V reference is 16 volts they have given. So V reference is 16 volt means, so it's a 4-bit of resolution. So each LSB will be 1 volt because 1 LSB is equal to what? 1 LSB is equal to Vref by 2 power n. Vref is 16 volt. 2 power n is 4. So 1 volt. This is the resolution, 1 LSB. For a change in 1 LS bit that has to occur, 1 volt we should increase in the analog voltage. That's what it is mentioned. Each LSB will be 1. So now if Vin equal to 2 volt, okay, Vin is equal to 2 volt. That means 2 power 4 means quantization level is going to be 2 power n combinations. 0 to Vref. So 0, 0, 0, 1 to 1, 1, 1. Okay, there are going to be 2 power n quantization levels. Okay, accordingly, we need, if Vin is equal to 2 volt means the output of the first 2 bit, since it's a 2-bit 2-step flash, 2 bit for MSB and 2 bit for so 2 bit if Vin is equal to 2 volt, the output of the first 2 bit will be 0 0 since Vref equal to 16 volt, and each resistor drops 4 volt, and the output of the 2 bit DAC V1 will therefore be 0 volt. So that's what Vin is equal to 2 volt means D3 D2 is going to be 0 0. So you can look upon here, this is going to be V1 voltage and this is going to be V2. This is V1 and this is going to be V2 and this is V3. You can tabulate the values. You can tabulate the values as V1, V2 and V3. And you can draw the diagram like the 0 to Vref. What is your 2 volt? If it is going to be 2 volt, what is your MSB? Right? So it is going to be lie in the range of 0 0 0 to 8. If you manipulate that one, so the for 2 volt it is going to be 0 0 1 0, right? Because we are having 2 bit resolution as MSB. So what I mean to say is 2 bit as MSB, but reference voltage remains the same. So this 16 volt, I am going to have realize it in 2 bit, right? 2 bit means 4 quantization levels are going to have, right? 0 0 0 1 1 0 1 1. Okay, so 0 that is going to be like 4 volt, 8 volt, 12 volt. Less than 4 volt means your digital bits is going to be 0 0, right? Fine. So this part will be again quantified as 0 0 0 1 1 0 1 1, like that. Fine. And then what is the V2 voltage? What is the V2 voltage over here? Okay, 2 volt. Fine. Based on that one, this architecture V2, V3. What is the V3 voltage? We should know 8 volt. So 8 volt means it is 8 volt 1 0. It is going to be 1 0. So it is going to be like in 1 0. Like that, the coarse and fine conversion value will be made. And again, for here also accuracy issue. Again, it should be less than INL and DNL. If you see, less than plus or minus half LSB. Okay, there are so many derivations. Derivations are there, fine, which we should know. Fine, these constraints we should know. Okay, for designing the op-amp, to design a sample and hold amplifier, for this ADC, how the op-amp specification has to be derived. What should be the gain of the op-amp and what should be the unity gain bandwidth of the op-amp we should know. So presently you can see that the gain of the op-amp should be approximately equal to 2 power n plus 1 by beta. Okay, beta is the feedback factor. Beta is feedback factor. If you are going to take it as in unity gain configuration, right, beta equal to 1 if you are going to achieve 2 power n, your open loop gain should be 2 power n plus 1. The gain of the amplifier should be greater than or equal to 2 power n plus 1. Okay, and to attain the sampling frequency, what should be your unity gain bandwidth? Okay, for designing op-amp, to realize the sample and hold circuit, the op-amp DC gain should be AOL equal to open loop gain. In open loop gain, it should be greater than or equal to 2 power n plus 1. Okay, right? Similarly, the unity gain bandwidth, UGB, it should be F log. What is the sampling rate you are going to use? Ln of 2 power n plus 1 by pi into beta. So approximately we used to say that it should be 4 to 5 times of the sampling rate. 4 to 5 times of the sampling rate should be your unity gain bandwidth. So these specifications and all, you can see it in Jacob Becker CMOS circuit design and layout, mixed signal circuit design and layout. Okay, mixed signal circuit, here you will find. Okay, if we design a 12-bit ADC that is clocked at 100 megahertz means, right, we need to use op-amps with unity gain frequencies of 286 megahertz. So almost 2.5 times. But generally we used to have 4 to 5 times. A good design, you use a larger FEU. If you see here, okay, a good design, ideally speaking, 2.5 or 2.8 times it's coming, 286 megahertz. 100 megahertz means 286 would be the unity gain bandwidth, but still a larger is. So 4 to 5 times we will use it. Okay, 4 to 5 times of the sampling frequency should be considered. Okay, should be considered for designing the op-amp. So in today's morning session, we have used folded cascode amplifier, telescopic cascode amplifier. Those amplifier will be used to realize this sample and hold amplifier. Are you able to follow? Are you able to follow? Fine. And still further reduction in number of comparators that we are going to use in flash ADC, we can go with pipeline ADC. Pipeline ADC, it limits the speed. Pipelining means what? We are increasing the latency. Stage by stage, we are going to process it. But after a particular n clock cycles, the output will come in a continuous manner. Okay. So the pipeline ADC architecture, if you go with the pipeline ADC architecture, sample and hold, this is the architecture of the pipeline ADC. If you are going to realize a 3-bit ADC, if you are going to realize a 3-bit ADC, so 3 stages will be there. So 3 comparators, only 3 comparators are required. Okay, 3 comparators. So, but we require 3 clock cycles to generate the output simultaneously. You understand? If you are going for a 10-bit pipeline ADC, 10 stages you will be having. So 10 comparators are required. So power consumption area, but 10 clock cycle is required to generate the output. Okay. So we will be doing this conversion, all those things for all the ADCs. The what do you call the area, power and speed has to be considered, and the accuracy issues also we need to consider. Okay, the accuracy issues also we need to consider. Fine. So these are all some familiar Nyquist rate A to D converters. Okay, Nyquist rate. Now to have an idea on a quick recap on the sigma delta oversampling converters. Oversampling converters. Right, I will go with. So oversampling converters means it is the sampling is done at a much higher rate. Okay, if Nyquist rate is 2f, whereas for sampling oversampling rate, your sampling is going to be done at a very higher rate. Why we are going for oversampling ADCs means mainly to increase the resolution, to increase the resolution of the ADC, to increase the resolution of the ADC. Okay, and at high speed, we can also realize a very high speed ADC using oversampling unlocked to digital converters. Okay, so in Nyquist rate converters, we require an anti-aliasing filter. In oversampling converters, we don't require an anti-aliasing filter. Okay, we don't require an anti-aliasing filter. And we don't require a dedicated sample and hold circuit. We don't require a dedicated sample. The sigma delta modulator itself will perform the quantization. Okay, right? So this is the sampling frequency. If 2 times, so exactly at Nyquist rate, if you are doing aliasing is going to be there. If oversampling means no aliasing is going to be there. Right? So based on that one, this is the first order sigma delta modulator. So sigma and then what you call this is delta and 1 by s is going to be sigma. Integrated is nothing but summation, continuous summation, right? So based on that, the architecture of the sigma delta modulator is shown over here. So here that since the modulator itself is going to perform the quantization, we are giving QE of s. So V out of s, we can write it as V out of s equal to QE of s plus 1 by s into here 1 by s into V in minus V out of s. V in minus V out of s into 1 by s. So QE of s, if you expand this, right? If you 1 by s v if you rearrange this for V out of s, you will get QE of s into s by s plus 1, and for V in of s, you will get as 1 by s plus 1. Right? QE of so for QE of s, what will be V in of s? We are going to make it as 0. Okay, we are going to make it 0 means V out with respect to QE of s, it is going to act as a pass filter, quantization noise. Okay. So the quantization, the textbook what I am referred is Jacob Becker, CMOS. I'll show you the textbook. CMOS circuit design. Okay. So quantization noise, noise will be filtered out. Okay, it will go to the high pass range, whereas for signal it will act as a low pass. That's why here the frequency response, if you see the bandwidth, the noise is moved to the high frequency domain. Okay, so the signal to noise ratio is going to be improved. The signal to noise ratio is going to be improved. Generally for Nyquist rate, the SNR is given as SNR is given as 6.02 n plus 1.76, whereas for this first order filter, if you see, I'll just go with the final equation. Here you observe that with first order modulator, 10 times of log of OSR, okay, oversampling ratio. So that means SNR is improved means n is going to be, the bit resolution is going to be improved. Okay, so there are a lot of data sheets available for our reference, right? For our reference in order to understand this sigma. These are all now in today's trend. As far as analog to digital converters, sigma delay, it will have high resolution. At the same time, discrete time sigma delta modulator, continuous time sigma delta modulator, two modulators are there. Continuous time will have high speed compared to discrete time sigma delta modulators. Okay, so with this information, I feel that I have touched upon all the architectures and the merits and demerits, how you have to visualize the architecture of the DAC and ADC. Okay, and how you are going to characterize the ADC and DAC with respect to INL and DNL. Okay, so the textbook what I have followed for this thing is so CMOS circuit design, layout and simulation, or Jacob Becker. So you can see, you can refer all the material, whatever I have taken is this from this textbook. If you see this resistor spring back, everything I have taken it from this textbook. Okay. So line by line, when you start reading, probably you will be in a position to further explore your thoughts on this architectures, and you can come up with a good publication. So I would like to thank the management and the faculties who have organized this workshop to deliver this thing, this lecture. If any questions, maybe you can ask me. With this, I will end my session. Any questions?
Anybody would like to ask anything? Any questions?
There are a lot of architectures. I have taken a few architectures only. So the topic of today's session, I felt that for the biomedical recording system, the preamplifier is one of the most important blocks you should know. And the ADC, what is the ADC you are going to use? We need high resolution because we are going to process the signal, biomedical signal, right? So we require high resolution ADCs. Okay, high resolution ADC with flash ADC, it's area, power, all those things is going to be increased. So we can either go with pipeline or we can go with sigma delta.
Any question from participants? Participants can write the question in chat box. So I think no questions are there. Okay. Thank you, sir, for giving a wonderful talk on CMOS amplifier and biomedical applications. And actually, starting from basics of amplifier and small signal analysis, you have covered a very good application for biomedical design. And then you showcase us the circuits and data converter circuits and its design. So thank you so much for sharing your time and experiences with us. I'm sure that benefited from your talk. Thank you, sir. And please accept a virtual memento as a token of thanks from our STTP team. Hello, sir.
Am I audible?
Yes, sir, you're audible.
If necessary, I will send this PPTs.
Yes,
PPTs
sir.
for
Yes.
reference.
Yes, sir. Yes.
Okay.
Yes, sir. Please send. We will put it on Moodle platform so that all participants can refer because they will have assessment also. They have their quizzes. Yes.
Okay. Okay, sir. Thanks a lot for providing me this opportunity.
Sir, thank you very much, sir. Sir, I should say thanks to you.
Okay.
Kumaravel, sir. Thank you very much. And we'll connect with you in future as well.
Okay.
Yeah, good.
Thank you, sir.
Thank you. Thank you, sir. Thank you very much. Thanks a lot.
Yeah, I'll leave the meeting.
Yes, sir. Yes. So participants, we will meet in the evening, 5 o'clock. We will have Miraj with us. He is research scholar at IIT Bombay. So he will be taking the session, evening session 5 to 7. So thank you very much. So I'll close the meeting, okay?
Yes, sir.